Large language models, or LLMs, are advanced AI systems trained to generate detailed reasoning traces for tasks like math problems, coding, and general problem solving. These traces are sequences of tokens that show the model's step-by-step thinking, which not only boosts the model's own performance but also makes it vulnerable to a technique called model distillation. Model distillation involves training a smaller, less powerful model to mimic the behavior of a larger, more capable one by learning from these generated traces. This process is efficient and effective, allowing the smaller model to achieve impressive results with far less computational resources than training from scratch. For example, companies like OpenAI have even offered distillation as a service through their APIs. However, this creates significant problems for the owners of these frontier models. First, by generating and sharing these reasoning traces, model providers essentially give away valuable intellectual property. Competitors can use these traces to replicate the model's capabilities at a low cost, undermining the original developer's competitive edge. Second, the ease of distillation might push model providers to limit user access, such as by hiding token probabilities or summarizing outputs, which could reduce the model's usefulness for legitimate applications. Finally, distilled models often don't inherit important safety features, like resistance to jailbreaking or generating harmful content, potentially leading to misuse. To counter these issues, researchers at Carnegie Mellon University have introduced a method called antidistillation sampling. This technique strategically alters the way a model samples its next token in a sequence, effectively poisoning the reasoning traces. The goal is to make these traces much less useful for distillation while keeping the model's overall performance intact for everyday use. At its core, antidistillation sampling works by modifying the model's probability distribution for selecting the next token. Normally, models use methods like temperature sampling to generate diverse and accurate outputs. But with antidistillation, the distribution is adjusted so that the generated traces still look plausible and maintain high likelihood under the original model, but they become misleading or suboptimal for training a distilled model. In experiments detailed in the paper, the researchers compared antidistillation sampling to standard temperature sampling on benchmark datasets like math and GSM-8K. These datasets test mathematical reasoning abilities. For the teacher model, the original LLM, the accuracy remained high under both sampling methods, showing that antidistillation doesn't harm the model's practical utility. For instance, on the math dataset, the teacher model's accuracy was around 80% with baseline temperature sampling and stayed nearly the same at about 58.75% and 58.58% under antidistillation sampling variations, depending on the specific setup. This demonstrates that the model's downstream performance is preserved. However, when it came to distilling a student model, a smaller model trained on these traces, the results were starkly different. With baseline temperature sampling, the student model achieved accuracies of about 14.50% on math. But with antidistillation sampling, this dropped significantly to around 12.62% or even 10.16%, making the distillation process much less effective. Similar patterns emerged on the GSM-8K dataset, which focuses on grade school math problems. The teacher model's accuracy was about 91.28% with temperature sampling and around 68.90% to 68.51% with antidistillation sampling, again showing minimal loss in performance. For the student model, baseline sampling led to about 60.71% accuracy, while antidistillation reduced this to as low as 24.73%, highlighting how well the method poisons the traces. These findings are illustrated in Figure 1 of the paper, which plots the accuracies for both teacher and student models under different sampling schemes. The key takeaway is that antidistillation sampling allows model owners to control for teacher accuracy while drastically degrading the student's performance, effectively protecting their intellectual property. The paper also situates this work within the broader context of related research. Model distillation isn't new. It dates back to ideas from researchers like Schmidhuber in the early days of AI, and more recently, Hinton and others have shown how distilled models can excel in various domains. Companies and labs have increasingly adopted distillation, with some speculation that certain commercial LLMs are trained using traces from competitors' models. This practice underscores a strategic vulnerability for frontier AI developers, as reasoning traces are highly valuable. By introducing anti-distillation sampling, the researchers provide a practical tool to mitigate these risks without compromising the model's utility for end users. In terms of implementation, anti-distillation involves subtle adjustments to the sampling process. For example, it might involve shifting probabilities to favor tokens that are less informative or more confusing for a distilling model, all while ensuring the output remains coherent and effective for the original task. This balance is crucial because if the modifications were too aggressive, they could degrade the model's performance, defeating the purpose. The paper emphasizes that this method is particularly relevant in an era where AI models are deployed as services, and users can interact with them to generate potentially exploitable outputs. By poisoning the traces, anti-distillation helps maintain the exclusivity of proprietary capabilities, such as specialized reasoning skills developed through expensive training processes. Overall, the experiments validate anti-distillation's effectiveness across different datasets, showing consistent reductions in distillability without significant drops in teacher accuracy. This approach could be extended to other types of models or tasks, potentially influencing how AI providers design their sampling strategies in the future. To wrap up the explanation of the key mechanisms, anti-distillation sampling represents a clever defensive strategy in the ongoing arms race of AI development, ensuring that the rich knowledge embedded in frontier models isn't easily transferable through distillation.